Light doesn't go faster because it can't. Not due to any weakness, flaw, or limit in energy, but because it's operating in perfect harmony with the laws of the universe. It obeys a cosmic boundary, a line carved deep into the structure of physics. One that says, this far, no farther. This speed limit isn't restrictive in a chaotic sense. It's constructive. It brings order, stability, and predictability to the cosmos. Without this limit, reality would collapse into nonsense. Time wouldn't flow properly. Events might occur in reverse. The universe as we know it would disintegrate into paradoxes. Instead, we have a universe where light travels at just the right pace, nearly 300,000 kilometers per second, to keep time flowing forward, causality intact, and scientific understanding within reach. For something that moves nearly 7.5 times around Earth in 1 second, it's a pace that feels not just fast, but graceful. And then came Albert Einstein, a quiet thinker with a mind tuned to the subtle whispers of nature. When he introduced his theory of special relativity in 1905, he didn't just adjust the physics textbooks. He ripped them up and started again. At the very core of his new theory was a bold, almost mystical statement. The speed of light in a vacuum is the same for all observers, no matter their motion. That was radical. Before Einstein, people thought time and space were absolute, that clocks ticked the same for everyone, and rulers measured the same lengths across all frames of reference. But Einstein shattered that idea. He proposed something strange. If the speed of light remains constant, then time and space must bend to preserve that truth. In other words, the universe would change the rules of time and distance depending on your motion, just to ensure that light always appears to travel at the same speed. Imagine this. You're in a spaceship, flying near the speed of light. You shine a flashlight ahead. You'd think the beam would appear to crawl away from you slowly. But no, you'll still measure it traveling at 299,792 km. To make that possible, your own experience of time would slow down. Your distances would compress. This isn't fantasy. These are measurable effects. Astronauts aboard the International Space Station age just a tiny bit slower than we do on Earth. Their clocks tick more slowly, not by much, but enough to prove Einstein right. So what Einstein did was establish a new language for the universe, one where speed, time, and space are all interconnected, and light is the translator between them. But he didn't stop there. Special relativity also brought us another profound truth. Mass and energy are interchangeable. That's what his famous equation E equals mc2 tells us. It means a small amount of mass can become a huge amount of energy. That's the principle behind nuclear power, and also behind the stars. Because of Einstein, we understand that the sun shines by converting tiny bits of mass into enormous amounts of light and heat. Every photon that hits your skin on a summer day was born from that sacred exchange of matter into energy. Now, let's go deeper. Special relativity is only part of Einstein's legacy. A few years later, he expanded his thinking to include acceleration and gravity, leading to what we now call general relativity. And here, light took on an even more astonishing role. Einstein showed that gravity isn't a force pulling objects together. It's a bending of space-time itself. And because light travels through space-time, its path bends too. This leads us to an incredible prediction. Gravity can bend light. We've seen it. Light from distant galaxies curves around massive objects like black holes, creating what we call gravitational lensing, a cosmic mirage where light arcs across the sky like liquid glass. Imagine seeing the same galaxy appear in multiple places because light took different curved paths around a massive object. That's not science fiction. That's our reality. And it's all possible because light follows the structure of space-time like a train on invisible tracks. So not only is light bound to a specific speed, it's also bound to the geometry of the universe. It moves along the curves and warps created by stars, planets, and black holes. The more massive the object, the more space-time bends, and the more light's path curves. And if an object is massive enough, like a black hole, even light can't escape. That's the ultimate boundary, a region called the event horizon, where space-time is so warped, every possible path leads inward. But more on that in the next segment. Here's what matters for now. Einstein didn't just explain how light behaves. He revealed that light defines the behavior of reality. Its speed determines how time passes. Its path reveals how space is shaped. Its energy tells us how stars shine. Light isn't just illumination, it's information. Through Einstein's eyes, we began to see that everything, time, space, mass, energy, is part of one grand equation, and light is the key that holds it all together. Let's take a breath and reflect. From curious astronomers watching eclipses centuries ago, to satellites measuring atomic clocks in orbit, to telescopes watching light curve around galaxies billions of light-years away, we've followed this single constant, light, and we've learned that behind its speed lies something eternal, a pattern, a harmony, a story told not in words, but in photons. At Infinity Beyond, we believe those stories deserve to be told slowly, clearly, and beautifully. In our next segment, we'll fall into the very edge of a black hole to witness what happens to light as it reaches a place where not even time can escape. Until then, let your mind bend with the stars.